Good. Okay, well, it's my great pleasure to introduce John Toth. He'll be speaking about lower bounds for eigenfunctions in Lagranary regions.
All right, well, thanks very much. I thank the organizers for inviting me to speak. I'm going to talk mainly about lower bounds for eigenfunctions on the quinary regions, which is a result of work with Shaiza Kansani. Before I do that, I know I have a short talk here, so I will go quickly, but I want to give a little bit of overview. It's not, I do not claim any of this to be, this is not complete by any means. I'm going to focus here on very specific things. In particular, I want to just discuss a few of the results on L2 restrictions of eigenfunctions. There's a whole family of results on LP, which I will repeat different than two. I will not talk at all about. So the basic problem is this: I have a compact closed Riemannian manifold. Again, I can allow boundaries for much of what I'm going to say, but let's just fix things for the moment. I take Laplace eigenfunctions. My eigenvalues are lambda j squared. So lambda j is 1 over h. I take an orientable smooth hypersurface. In some cases, h can be higher codimension, but for most of what I say, we'll just take codimension 1. And the basic problem is, okay, estimate the L2 restrictions, estimate the L2 integrals of the eigenfunctions and restrict it to h. D sigma here is just a natural induced measure on the hypersurface, right? So why do we want to do this? Well, I sort of think of it this way. One issue is to understand quantitative unique continuation along hypersurface. This is what we call goodness estimates with Zeldich. I'll talk a little bit about that in a minute. Issue of how, whether or not we can extend sort of ambient quantitative unique continuation that you get from Kalaman estimates to restrictions to the hypersurface. That's a rather interesting and challenging problem. The second is to extend equidistribution results for eigenfunctions, so QE quantum ergodicity type results to hypersurfaces, what we called with quantum ergodic restriction. And the third is simply the fact that while restriction bounds play an important role in the study of asymptotics of eigenfunction nodal and critical sets. So I want to say a little bit about these things first, and then I'll get to the recent results with Shaiza. Okay, so let me discuss upper bounds very quickly first. Again, it's not a complete list of anything. I just want to discuss some of the main results. So in the case where you have Laplace eigenfunctions, Berkshire and Svetkov prove LP upper bounds for arbitrary p. In the simplest case where dimensions 2 and p is equal to 2, what you get is that the L2 restriction is lambda to the 1/4, over lambda to the 1/4. Well, this is sharp, right? So if you take highest weight spherical harmonics, like I've given here, phi sub n, which is some universal constant times n to the 1/4, x plus I y to the nth power, then you see that if you take h to be your equatorial geodesic that I pictured here on the bottom of the page, right here, these things concentrate very sharply on h. They decay exponentially off of h. And if you just compute the L2 restriction, you'll see that it in fact saturates the bound in 2. So you can't improve such bounds in general. Note, however, that H is a geodesic. It's a periodic geodesic in this case. In the case where H has positive geodesic curvature, so it's, for example, not a geodesic. So if you go back to this picture here, you could take, for example, a latitudinal circle that's off the equator, right? If you take such an H, then you can improve the L2 restriction bound to lambda to the 1/6. And again, this is sharp. And this was already proved in Berkshire and Svetkov. I should point out that Hassel and Tacey, after the BGT paper, they generalized these results to LP restriction bounds to general Schrodinger operators. And there are some sort of very large improvements that are known in some specific cases. For example, in the case of flat tori in dimension 2 and 3, Borgen and Rudnick show that for positively curved hypersurfaces, the L2 restrictions are comparable to 1. So they're uniformly bounded by a constant from above and uniformly bounded by a constant from below. And for arithmetic surfaces, there are explicit polynomial improvements. I'll say a little bit about this in a minute, a little bit more about this in a minute, but that were proved by Gosh, Reznikov, and Sarnak. For example, in the case where H is a horocycle. There are some additional improvements that I proved in quantum completely integrable cases, and also log lambda improvements in negatively Kerr case that were proved by Blair and Sog. So again, it's an incomplete list, but these are some of the known results for L2 restrictions, at least upper bounds for L2 restrictions. So what about the issue of asymptotics or quantum generalizations of quantum ergodicity to hypersurfaces? Well, so let me quickly go over what's known here as far as I know. So if I'm given an L2 normalized sequence of eigenfunctions, we say it's quantum ergodic or QE. If for any zeroth order symbol, the matrix elements op A phi lambda tend as lambda goes to infinity to the integral of A with d mu L, where d mu L is Liouville measure. So this is equidistribution, right? And of course, the celebrated theorem on quantum ergodicity says that if I have a compact closed Riemannian manifold with ergodic geodesic flow with respect to Liouville measure on the cosphere bundle, then I can find a density one subsequence such that the density such that the density one subsequence is QE, right? And so here's a picture. It's a kind of a putative plot of the density plot of a QE eigenfunction on a stadium, Bonnemoid stadium. And I pictured here a curve, let's say strictly convex curve H, which I'll refer to in a minute. So what we're basically looking at are the restrictions of these eigenfunctions to such an H, and we're trying to estimate from above and below the L2 restrictions. Okay, so the basic question that Zeldich and I studied was, well, does the QE theorem above for the ambient manifold, how can one generalize? How can one extend this to hypersurfaces and manifold? And so what we proved was that if you have a compact manifold with ergodic geodesic flow, and H is a hypersurface that is asymmetric with respect to geodesic flow, then indeed I can find, I'm not going to define this precisely, but basically the asymmetric condition rules out cases where, for example, H is the fixed point set of an isometric involution or something like that, where QE cannot hold, the restricted QE cannot hold, QER cannot hold, because half the eigenfunctions would be zero, the odd ones, and half would be even. So we have to rule out situations like that. But assuming that's not the case, it's asymmetric, then indeed there's a QER theorem. It says that if I look at the restricted eigenfunctions along such an asymmetric hypersurface, the matrix elements tend asymptotically to the limit, which is the integral of the symbol over the, if you like, you can rewrite this as just the integral over the cosphere bundle of M with foot points on N. Footpoints on H with respect to the induced Liouville measure, the restricted Liouville measure to the cosphere bundle of M with footpoints on H, right? So it's an equidistribution result that's a straightforward analog of QE. So this result does apply to, in the case where, for example, H are geodesic circles, closed horocycles, and generic closed geodesics on hyperbolic surfaces. This result was extended by Dyatlov and Zavorsky to the semi-classical Schrödinger case and arbitrary manifolds with boundary. Unfortunately, the density one subsequence that we have to extract here in this QER sequence, in this QER theorem, well, we don't know whether it agrees with the sequence of QE eigenfunctions on the ambient manifold. So you might have to extract different density one subsequences. So this turns out to be a rather delicate issue, and as far as I know, it's still open. So given a QE sequence of eigenfunctions, the open question is under what conditions on the manifold, the hypersurface, and the metric do the restrictions satisfy QER? And as far as I know, this is still very open. Another sort of kind of result dealing with equidistribution deals with equidistribution of Cauchy data. So this is a simpler problem, and the result is maybe a little bit more direct. So QER theorems for Cauchy data. So what is Cauchy data? Well, we simply denote this, we simply consider the two tuple of, well, we look at the eigenfunction restrictions to H. Phi sub H here is, I'm shifting the semi-classical notation. And the second slot is the normalized normal derivative of H, of the eigenfunctional restricted to H. Again, I multiplied by the Planck's constant H here just to make sure everything is semi-classical order 0. So that's sort of the Cauchy data. Then what we proved with what I proved with Christensen and Zeldich is that if you have any smooth codimension 1 orientable separating hypersurface, say an interior, and if I have any interior QE sequence, then automatically the restrictions of the Cauchy data associated to that interior sequence automatically satisfies the QER theorem that I've stated here. So in this case, of course, the matrix elements involve the sum of two terms, one involving Neumann data and the other one involving Dirichlet. The result holds for all interior hypersurfaces and generalizes early results of Hassel and Zeldich and Burke in the specific case where H is the boundary. Okay, so these are sort of the basic results on equidistribution that are known. So that brings me to sort of really the main thing I want to talk about, which are lower bounds. So here again, there's some special cases that are known. So if M is a flat torus, I've already alluded to this, in dimension 2 and 3, and H is positively curved, then Bourgain-Rudnick theorem says that the L2 restrictions are comparable to 1. So in particular, L2 restriction is uniformly bounded from below. When you have an arithmetic surface, sorry, it should be gamma. This is an arithmetic surface. The second, there's a typo there. But if I have a closed horocycle, then Gauss-Reznikov-Sarnak proved that, in fact, we have this sort of comparability estimate. So basically, the L2 restriction is, H bar epsilon from below and H bar minus epsilon from above. So very, very large improvements over the Birkschott-Svetkov upper bound, for example. And even the lower bound is essentially very arbitrarily close to uniform boundedness from below. With Zeldich, we showed that under geometric control assumption on the hypersurface, in particular, when M is, so when the geodesic flows are ergodic, but this applies in a much more general setting. So for example, there are quantum completely integrable situations where this is satisfied. Then under such a geometric control assumption, we proved that for an arbitrarily large density, so an arbitrary density, arbitrarily close to 1, one has a uniform lower bound for the L2 restrictions. Finally, I should point out that in case of Cauchy data, when M is a negatively curved surface and H is a smooth curve, I guess with positive curvature, I should put that in. Then Galkov, you don't need that. So when M is negatively curved and H is any smooth curve, using the estimates of Dyatlov and Jin on the ambient mass of eigenfunctions from below, Galkovsky and Zeldich have recently showed that there's a uniform bound for the Cauchy data from below. So, and this holds for all eigenfunctions. So there's no restriction necessary, simply because the ambient estimates from Dyatlov and Jin work for all eigenfunctions. Okay, so these are sort of some improvements and some known explicit results. But the point here I want to make is that in general, estimates of the form, so uniform bounds from below, are way too ambitious. In fact, even polynomial estimates are way too ambitious. So why do I say that? Well, even if we consider the ambient problem, so if I take an open subset of the manifold, so dimension n, if M is dimension n, then it's well known that the L2 mass is exponentially bounded from below, and that's the best you can do in general. This is quantitative unique continuation, and it's proved using Carlin estimates. So when you restrict the hypersurfaces, there's no way you can expect for better results in general, right? This is the best you can hope for. So the natural question here is, are there analogous statements for eigenfunction restrictions and arbitrary hypersurfaces? More precisely, given a hypersurface, can you find a constant, depending on mg and h, and possibly the subsequence itself, such that the L2 restrictions are exponentially bounded from below? Zeldich, we called such an estimate a goodness estimate. The answer is no in general, because again, you have this sort of situation where, H could be a geodesic on a surface that is invariant under an orientation reversing Z2 isometry. And then, you have half the eigenfunctions being identically zero. So obviously they're not bounded from their, well, the L2 restrictions are just zero. However, it's still an interesting question. The question is, can we prove this in some interesting cases? So as far as I know, one of the first results along these lines was a result by Zheng, showed that if H is a geodesic circle or closed horizontal on a hyperbolic surface, then it's exponentially, the restrictions are exponentially bounded from below. About 10 years ago or so with El-Haj, I showed that if you have a sequence of Dirichlet-Neumann eigenfunctions that are interior QE, and if I take any strictly convex analytic interior curve, then I also have goodness estimates. So for example, if you go back to this picture here, right? So it's what our theorem with El-Haj says: if you take a QE eigenfunction, so something like in the picture, and you restrict it to H, the L2 restrictions are exponentially bounded from below. And I cannot prove anything better than that. So as an example, our results apply to things like the Wunamovitz Stadium and other ergodic billiards. Okay, so that brings me sort of the final point here, dealing with the sort of the rationale that I talked about at the beginning, the issue of nodal and section bounds. So if you look at the nodal set, which is Z sub phi H, zero set, and if I take a fixed interior curve, so I'm dealing here in dimension 2. We discussed the generalization of this result with Zeldich in a recent paper to arbitrary dimensions. But let me take the simplest case, a nodal domain. So if I take a piecewise smooth planar domain and I take an H and real analytic interior curve, and suppose the sequence of eigenfunctions satisfies the goodness estimate, so it's the L2 restriction is exponentially bounded from below, then the number of nodal intersections is at most H to the minus, O of H to the minus 1/2. So it's at most the fundamental frequency. So the picture here is you take an eigenfunction with the zero set given with the gray lines, and you take some fixed curve, let's say H with blue, and you count the number of intersections. And if you have a goodness estimate, then there's an upper bound on the number of intersections. All right, so what we did with Scheiße was we considered the case where you take a particular subsequence, normalized eigenfunctions, and we considered the case where there's some defect measure associated to that subsequence, and we considered the case where that defect measure is localized. So it's definitely not QE. It's very much not QE. So I'll explain that in a minute. But so you take a sequence of eigenfunctions, always L2 normalized with some defect measures. So this measure is a probability measure invariant under the geodesic flow. In the QE case, it's mu sub L, which is a Liouville measure. Here we're dealing with very much the case where we're very much not QE. So what we do is we make a couple of assumptions. So we're going to assume here that the defect measure, the push forward defect measure, is localized in the sense that the support is not all of M. So there's some complement, right? That we'll call that the localization condition. And then we assume that there's some sort of control condition. So there's some point in the support of the push forward measure and a ball centered at that point such that the ball is disjoint from the hypersurface and the mass over the ball is uniformly bounded from below. So there's some control assumption that's necessary. So the simplest case here is I have some hypersurface that's sitting inside the complement of the support of the push forward measure. And I take a thin Fermi tube around the hypersurface, which is also disjoint from the support. So the picture here looks like that. You've got the blue set, which is the support of the push forward measure. You've got some red ball here where I know there's mass from below. So that's some sort of control condition. And then I've got a hypersurface in black outside, and I've got a green thin Fermi tube around it, which is also outside. So this is all motivated by the Schrodinger case, in particular forbidden regions in Schrodinger case, which we discussed in earlier work, but is much more general than that. It's nothing to do with Schrodinger operators, really. It's It applies, for example, in quantum completely integrable situations, in arbitrary dimension where you need not have a Schrodinger operator, and even other examples as well. So we make these two assumptions, localization, control, and then we need what we'll call a lacunary operator. So we take a thin Fermi tube around H, and we assume that there's an analytic pseudodifferential operator. And we'll call it lacunary if, well, it satisfies a complex principal type condition, which again is motivated by the Schrodinger case. I don't want to explicitly say at the moment what that means. And in addition, if you apply to the eigenfunctions, well, you get exponentially small L2 mass over the Fermi tube. And the constant here, the C1, is taken to be uniform. So it depends only on mg and mu, where mu is a defect measure. So in particular, it's uniform independent of h in some fixed, so it does not depend on the distance to the control ball, for example. So what is the model example here? Well, again, it's the Schrodinger case. Here, in the Schrodinger case, the lacunary operator is actually just the Schrodinger operator itself, right? So where V is a real analytic real potential, E is a regular value. You take the support of the push forward measure, it's contained inside the allowable region, V less or equal to E. H is taken to be some hypersurface in the forbidden region. Notice you can factorize the symbol of Q in this way, right? In the first term, the square root of the B symbol, which is the first thing, the square root of psi prime squared plus V minus E. It's obviously elliptic in the tangential psi prime variables, and the second factor A, which is this thing here, this is again elliptic in all of the variables. So this sort of motivates very strongly what we want to prove. And notice this satisfies a complex principal type condition that I won't state here, but it's modeled on this. It's basically if you complexify the frequency variable psi into zeta n, do the complexification of Q to the holomorphic continuation, then the zeta n complex derivative of the holomorphically continued Q does not vanish on the complex characteristic variety. So it's a natural analog. That's why we call it principal type condition. That's obviously satisfied in such an example. So what's our theorem? The theorem says that if I have a compact real analytic manifold, any sequence of eigenfunctions with a defect measure that is localized, and I have a control assumption. If I let H be any closed hypersurface, real analytic hypersurface, suppose that I assume that there's some thin Fermi tubular region about which there is a lacunary operator for the subsequence, then I have an exponential lower bound. And the exponential lower bound, the factor depends only on distance of the hypersurface to the point Q, where Q is the center of the control ball. So here I'm taking the distance of the green, this distance of the black hypersurface to the center point here of the control ball. So that's goodness. So maybe, very quick sketch. So it's modeled again by the Schrodinger case, right? So what I have is a factorization result. So I factorize the symbol. So what do I do? Well, what we show is that in the Fermi tube, we have a factorization. We can factorize Q, which is the lacunary operator, as an elliptic H bar pseudo A times sort of this kind of thing. So H bar ddxn plus I b hx d prime. So if you look at the Schrodinger case, this is B, right? And this is A, right? So there's your factorization. So in general, this factorization holds in general under these assumptions, and you have an exponential error term where again, the exponential factor, the constant here is uniform. Depends only on mg and the defect measure. And B here is elliptic in the tangential variables. Notice it's a pseudo in the tangential variables only. If you go back here, you see that, right? This is your B. It depends only on psi prime. All right, so since A is elliptic, I know that by assumption Q of UH, when you hit the eigenfunctions with Q, you get exponentially small behavior. So I can apply the parametrics for A. A is elliptic, and what you get is a diffusion equation, right? That H bar ddxn plus IB, a pseudodifferential operator acting only in the tangential variables applied to the eigenfunctions, is exponentially small. And the constant here is uniform. It depends only on mg and the defect measure. All right, so what do I do? Well, basically, I just integrate. So if I use this diffusion equation, if I take the normal derivative, so here I look at a family of hypersurfaces indexed by tau, where tau is just the level set xn equals tau. So h is xn equals 0, right? So if I just differentiate and I just apply the diffusion equation, what you get is a very simple equation. You get this equation in star. So what I do now is I just integrate over this little thin little Fermi tube around h. Right, and when you do that, you use the fact that you have guarding estimates tangentially because B is elliptic in psi prime. So you've got guarding estimates for the B term on the right-hand side of star. You integrate and you get double star, which is a very simple identity. So this directly relates L2 restriction along H to L2 restriction, sorry, to the L2 mass in the thin Fermi tube on the right-hand side, double star. The final step, which is I'm not going to get into here, but involves an explicit Carleman type estimate using the control assumption to bound the the first term on the right-hand side of double star by the exponential from below. And since this exponential, so if the hypersurface is close enough to Q, this distance term, the error term in double star can be absorbed into the lower bounds you get from Carleman. And that's basically the proof of the theorem. So I'm leaving all of the details out there, which there are many examples apart from Schrodinger, including QCI examples in arbitrary dimension, hyperellipsoids, Lyman oscillators where this applies, in addition to non-QCI examples as well. The basic question we're working on is right now is whether we can extend this argument, some of the ideas in this argument to deal with the cases where H intersects the support of the push forward measure. So it's, and we have some preliminary results, but maybe I'll stop there. Okay.
Are there any questions?
I guess I have a question. I'm just trying to understand a little bit your proof. Can you go back to what this H minus epsilon is and what, you go back a couple slides? I wasn't sure I quite got what that was. You know, how you get this, you have to share your screen again.
Yeah. Where?
Go
Where do you
back one slide. Wait, up forward a slide. Forward a slide. Next slide. Where the diffusion equation is. I think I understand what happened, but I'm not quite sure I understand. Next slide. So in the forbidden region, you have a diffusion equation, and in the allowed region, you would have a Schrodinger equation. Is that what happened?
Well, no, I'm not saying anything about allowed. Yeah, in the allowed region, it's not this. You know, you have a real principal type condition, so you definitely do not have this. You don't have ellipticity you don't have diffusion. Yes, you have a Schrodinger. You have a.
So that's how you got actually a better result in the forbidden.
Yeah,
region.
exactly.
It's actually even known in the allowed region, right?
No, because you see in the allowed region, first of all, no.
Oh, I see what you're doing. You're integrating over the level sets of the xn. That's what it is.
Yeah, exactly.
Yeah, sure.
Yeah.
I see. Yeah. Where did you use the control condition?
Carleman, which I haven't proved at all here. That's not trivial, but you have to. If you don't have a control conditions, you have no input into Carleman. You need some mass somewhere, right? You can't.
So you mean you differentiate the L2 mass along like?
Yeah, exactly. That part is straightforward. What isn't straightforward is the Carleman part. To get the explicit exponential, I haven't. That involves quite a bit of, tinkering, but it's true.
Okay, thanks.
Are there any other questions? If not, let's thank John again.